Welcome back, everybody, to the afternoon session and of the workshop. We have 4 speakers now, and first one is Antonio, and he's gonna talk about tracking the evolution of dynamic networks via indirect sampling. Let's take it away.
Can you hear me? Hear them remotely? Okay. First thing is, let me apologize for saying dynamic networks in the title, when I know that we all know that it's temporal graphs. This is a kind of a second part of a talk that I gave in this workshop 2 years ago, kind of describing the new result that we have obtained in a model. So I apologize for those who are familiar with some slides already. And also, it's kind of similar to a talk that I gave like a month ago in a DAX2 workshop. But I hope you like it. Some things have changed. Okay, this doesn't seem to work. You have to. No. Yeah. So yeah, although many people, including myself, don't want to remember this, but I always start these talks. Talks about the model that we use with this slide or this story. I go back to the day before Spain went into lockdown in 2020, when the front page of the main newspaper in Spain was saying that there were 3,000 confirmed cases of COVID in the country. The question is how realistic was this number, which was probably, everybody knew it was not real because there were not enough PCR capacity to test everybody. However, nobody knew how bad or how wrong this number was. Nobody knew whether we were talking about 30,000, 300,000, 3 million. So on that morning, I decided to come up with some technique that could be used to estimate roughly what was the situation. This is the current number, official number of people that were that had COVID on that day, March 14th, in Spain, 6,000. So this is not going to change. From the official figures, this is the final figure. So what we did is we deployed a Twitter survey in which we were asking people how many of your contacts have symptoms of being sick of COVID, okay? And well, Twitter didn't allow us to have more than 4 options. So we said 0, 1, 2, and 3 or more. And we translated that into how many cases they were reporting, assuming 3 or more meant 3. So essentially, out of the 700 plus people that answered, they were reporting 374 cases. In order to translate that into a ratio of the population that was infected, we had to know how many people each of these 700 respondents knew. So for that, we use 50, which is one of the circles, the size of a circle called Friends by a sociologist called Robin Dunbar here in the UK. He kind of describes several social circles. 50 is one of those, and we thought that was like the appropriate number. So by doing that, with a very quick math calculation, we obtained an estimate of 1% of the Spanish population being infected, which meant 500,000 people, roughly, which is 2 orders of magnitude higher than the official figures. How close was this to the reality? Well, we didn't know how to do it because there was no ground truth. So we tried to reproduce a ground truth by looking at how many fatalities were observed and trying to undo, based on fatalities, what was the number of infections. So it was known from Wuhan that roughly 1.38% of the people who were infected and had symptoms ended up dying, and roughly 2 weeks after. So we went 2 weeks after this date, and used the official number of roughly 6,000 deaths, and by applying simple rule, our estimate was of 433,000 infected 2 weeks before. So as you see, these numbers were quite close, and that inspired us to continue working on this. And in fact, we deployed a survey that was available for the whole world. It was translated to 70 different languages, and it was running for almost 5 years. And what we were collecting in this survey was what is called in the literature aggregated relational data. This is a technique that we reinvented, which is asking questions not about themselves, but about their contacts. How many of your contacts have property X? And to use that to estimate a hidden population, a population that is not easy to count, right? What is good about these kind of questions is that they are good for privacy. You're not answering about your own situation. You are answering about your group of friends. It reaches more people, because if I ask 100 people and each of them is answering about 100 more people and reaching 10,000, the problem is that the responses can be very, very biased. And in fact, this is something that has been observed. Anyway, so if you are curious, you can take a look at our website, coronasurveys.org, and see what we got. So once we collect this data, in particular, as you see, we have 2 questions, which how many people you know and how many of them have symptoms. You can estimate using different statistical methods. These are the 2 main methods that we used. One is just a ratio of how many people the participants know that are infected, divided by how many people they know, or the average of those ratios for the whole sample. This is, as I said, is not new. We reinvented it, but the very first studies were done in the 80s. In fact, the very first time, as far as we know, that this method was used was in the earthquake in Mexico City in 85. And the first paper, as far as we know, is from 89. So it's a technique that has been around for some time, but not too much, less than 40 years. And as you see, it has been mostly used for estimate populations that are hard to reach. Casualties in an earthquake, female sex workers, probably if you ask directly, they will never admit they are. So this has been effective. And in fact, it's been used by the UNAIDS department to estimate the prevalence of AIDS in Africa. However, what we found out is that there's very little analytical work on this method. In particular, the first thing that everybody was telling us when we were explaining what we were doing is say, oh, but what if 2 persons know the same sick person? You will be over-reporting. Well, we did some simulations. We observed that in general, things are okay. Even if there is overlapping between contacts, things the error is not very large. But that led us to question ourselves, how bad these estimates can be. The statisticians didn't do this effort, so we did it as computer scientists, theoretical computer scientists, right? So let me present you 2 different graphs or networks. Their topology is exactly the same, but I'm assuming that the orange nodes are the population that we want to count. Okay, so on the left, there's only 1 node in the population. On the right, roughly half of the nodes belong to the population. Okay, so what happens if we ask these nodes exactly the same questions that we were asking people in our survey? How many people you know in general, in total, and how many of them belong to the hidden population? What we observed is that in both cases, the answers are exactly the same. Every single node is going to tell you the same thing in both scenarios. Okay? Observe that I'm asking every single node. So I'm sampling the whole population. I'm not taking a small sample. I'm taking the whole population. Still, I don't know in which of the, just by looking at the answers, I don't know in which of these two cases I am. That leads to a theorem that says that, no matter which technique I use, if I use a deterministic decision, I may be wrong up to a factor of square root of n over 2, which is, as you imagine, quite bad. Good news is that if we introduce randomness in our network, that doesn't happen. So we're going to construct a network in which I let the adversary to deploy the hidden population before connecting the network and select the degree of every node in the network. It's a directed network where an arrow from node U to V means that V knows what the status of U. Okay? So I'm letting the adversary to choose the degree of every node, the in degree of every node. Okay? And all I do is whenever I have a degree, I just put the connections, select the connections uniformly at random from the rest of the network. Okay? If I do that, essentially this is the initial deployment. The adversary was the one who chose the colors, and it chose a degree of 3 for that blue node, and I just selected at random the 3 connections. And I do the same with everything. And then I take a sample of size m, uniformly at random again, and I ask the same 2 questions. How many neighbors do you have? What's your in degree? And how many of them belong to the hidden population? Okay. I use the 2 estimators again. And what I observe by simulation, I just run, these are simulated scenarios. I'm simulating an Erdős-Rényi network with actually many. We generated several. Erdős-Rényi network with 1 million nodes each, and a scale-free network with 250,000. What we observe is that the probability, the error that you obtain with only 100 nodes in a network of 1 million is already quite small, like less than 10%. And it doesn't change much depending on which of the 2 techniques you use, MOR or RLS, more or less. However, when we move to scale-free, the performance is worse, and we see a difference. In general, we're going to see that ROS is a little bit better than more in performance. But bottom line is, it works quite well if things are random, and we can prove it. We had to come up with our own version of the Chernow bounds, because what we have is a collection of random variables that are not independent. We know that they can be overlapping, so there's no independence. But we observed, we were able to bound the probability of the error being larger than 1 plus epsilon, and is an exponentially decaying probability with the size of the sample, which leads to this third result down here, which is that you can obtain with high probability an estimate whose error is less than epsilon by only selecting a logarithmic sample, a sample of logarithmic size. Okay. So now, so far, no temporal graphs. Now let's move to time. Let's introduce time here. Okay. So as in our algorithm, in our survey, we were collecting surveys over time. As I said, we run surveys for almost 4 years. What happened is that very quickly after we started using our survey, we contacted Facebook, or Facebook contacted us to let us know that they have a survey in which they were collecting more than 100,000 survey responses per day. So we decided not to invest too much in our own survey, because they were already collecting so much data. So what happened is that Facebook, in collaboration with Carnegie Mellon and the University of Maryland, they stopped their survey in June 22. And at that point, we had funding, so we decided to use that funding to recruit volunteers using a platform in which you pay people for filling your survey. And that's what we started doing in July 22. So in July 22, what you see here, this red line here, is data that we're obtaining by paying people to fill the survey that I show you, okay? The blue line is the official data. This is data from Portugal. And the yellow line is what we're obtaining, our estimate of infections from the Facebook and the University of Maryland survey. As you see, over time, we're capturing well the trend. And in fact, we are following quite nicely the curve that they were already capturing. However, they were collecting 12,000 responses a week while we were collecting 200. So in terms of cost, that was a huge difference. So if we move to a system in which we have a temporal social network, so essentially we have a network that changes in topology, changes overall, changes who is infected and who's not, who's in the hidden population and who's not. But we assume that the average in degree doesn't change. And the fact that an in-neighbor is in the hidden population doesn't depend on a degree. We have the following theorem. The expectation of the number of neighbors that are in the hidden population of a randomly selected node is the average degree times the prevalence of the COVID in this case. That means that you don't need, if what you want to study is the trend, how the signal evolves over time, and not necessarily the magnitude, the exact value, you don't need to compute the mu there. If you want, you can compute mu and then use it all the time. Assume that it doesn't change. But mu, the average degree, is not necessary to estimate the trend. We have a couple more results in that line of work, but I don't have time to go into that. So what I was showing was mostly done for COVID. But there's no reason why we should stop in COVID, and there's no even reason why we should stop in social networks. So we're going to apply, or we are applying it. This is a work in progress. We submitted the paper. We were already rejected twice. Sorry for that. Well, we are very sorry for that. We are applying the same ideas for a structured peer-to-peer networks. How many of you know what Kademlia is? Okay. A structured peer-to-peer network is a distributed dynamic system that implements a key value store. Key value store essentially is a database, or if you want, is a table in which you search by a key. Okay. And in a distributed way. So you have many peers, and they collaboratively implement this key value store. Essentially, the structure is like a random temporal graph because the nodes that form the peers join and leave. So it's completely dynamic. And the connections between them, because there's a graph, underlying graph, and the connection also change over time, even if they don't come and go. Okay? So it's a random temporal graph. I'm going to be focusing in Kademlia, which is one of the most popular. And right now, Kademlia, or a version of Kademlia, is being used in BitTorrent, in IPFS, in Ethereum, and originally in Emule. So these systems probably are familiar. The technology behind was very popular in the early 2000s, seems to be not that familiar. That's why I introduced a crash course on Kademlia. Essentially, how Kademlia works, and most of these structured peer-to-peer networks work, they have an identifier space very large. We're talking 2 to the 256 different identifiers. Okay? Originally, it was less, but this is the typical value that is being used now. And you have computers, peers, that are willing to help, and you have resources that you want to store in this key value store. So what you do now is you assign peers to these identifiers by applying a hash function, maybe to their IP address, and you also assign to the same space resources. Okay? This the ID assigned to the resource will be the one that you need to know in order to search, because you're going to be searching for that particular ID. So it could be the hash of a file, for instance. You know, you don't need to have the file, but somebody gives you the hash of the file, and then you can just go ahead and do the search. So in this particular case, now what you need is every resource has to be assigned to one peer. So the peer will keep a copy and will be the one responsible for, serving the resource. In particular, here you see the colors. The colors correspond to which peer takes care of a given resource. How do we create the network? The network, or the links in this topology, is peers. Every peer has buckets, and the bucket is just a list of neighbors. And as you see, the buckets are indexed by common prefix with respect to your neighbor. So for instance, this is the bucket of this guy, the 00111. There's no neighbor green, there's no neighbor yellow. The green neighbor is the one that has a common prefix of 4 bits. The ones in yellow are, without the ones that are already there considered, the ones that have 3, 2, 1, and 0. No common neighbor. And the number of peers that you store in your bucket is limited. I'm showing 2, but it could be typically 20. So this is essentially the network that you're creating. And the nodes, of course, is dynamic. The buckets can change over time, and blah, blah, blah. These are going to be my samples. So I'm going to be asking peers, about their buckets. Please provide me with your buckets, and in particular, give me your IP addresses, the IP addresses of your neighbors. When I want to find something, if I'm in the green peer and I'm trying to look a resource that is taken care by the destination peer, I send it. I have the ID of the resource, so I always send it to the closest, the one with the largest common prefix from all the neighbors I have in my bucket. So I can, do like this, for instance. So what we did is we collected, essentially, Kademlia is being used by Interplanetary File System, IPFS, which is a very popular storage for blockchains and other services. And what we did is we crawled, well, not us, it was Leo, our collaborator for TU Darmstadt. He crawled the whole network 12 times per day for a month. So we have 360 snapshots. So if you are interested in having real temporal graphs, we have temporal graphs. And we also operated 10 local nodes, local peers. So he deployed 10 peers in his own computers in Germany to be part of the network. Okay? Then from the IP address of a given node, we can extract which country that node is supposed to be by using some database, and whether it is in a cloud or is not in a cloud, and in case it's in a cloud, a popular cloud, which popular cloud it is. So this is what we obtained by taking this one snapshot. So no temporal graph here. So we took one snapshot and we went to 10 random nodes. Actually, this is the average of several such samplings. We took the 10 random nodes, we got their buckets, and we used that to estimate how many of them are in different countries or in different clouds. Now, temporal, we see that we can also estimate how it evolves over time. And the full crawl is like the golden truth, the real truth, ground truth. While the Moore and Ross, as you see, can follow the evolution quite nicely. Also, when we're looking at whether we're in a cloud or we were not in a cloud. Now, when we look at the 10 local nodes that were deployed, we obtained relatively good results in the static version, but in the dynamic version, as you see, there's no such a good matching, and we're still exploring why that happens. But well, it's work in progress. But as I said, this is a temporal graph. It's a real temporal graph. We have snapshots. If anybody wants to play with that, like modeling how peers arrive and leave, modeling how links change over time, we can work on that together. We are applying these techniques also to other things, for instance, to elections, and we actually got good results. But my time is up. So these indirect surveys are useful. They are not so well explored, especially when you look at time and space. You know, most of the work that we saw when we started the COVID experiment was in one location, one shot. Okay, very often even with paper. You know, they were just deploying the survey with papers and collecting it and using Excel to compute the experiments. So there's many things to be done. Yeah, I would like to see how we connect this line of work with temporal graphs, like for instance, how to model the node arrival and departure, then the creation of and removal of links, whether there are some, if we assume that the graph has some parameters, I mean, it's of some class, we can estimate the parameter of that class, anything. Okay, and well, we have a few papers published, but if you want to contact me, thank you.
Thank you very much. Are there questions? Yes.
Thanks for the nice talk. So going back to the first slide, essentially, so that the result on the standard methods, how wrong they can be, is essentially a worst case result, right? So you fix your underlying graph and you show that for the same observation, the underlying truth can be very different. And you don't assume like the sample is uniform or the network is uniform.
We don't assume what?
That you are sampling uniformly at random.
No, we're sampling the whole network.
Yeah. For the, but no, in the first slide.
Yeah. The worst case, the square root of n bound we get is for full sampling. We ask every single node in the network. Let me. Yep. You see?
Yeah. So you are asking all the nodes in the VC set, right? So you are not sampling the VA set.
No, I'm sampling everybody. VA, VC, and S. Everything. Everybody.
Okay. Then that answers my question. Okay.
Everybody. No, that's the point. The point is that everybody, if you see everybody in every set, is answering exactly the same. For instance, we don't know whether there's a similar result for dynamic, for the temporal version.
Are there any Any more questions in the audience here? I'm checking also. Yes.
Antonio, thank you for the presentation. Did you manage to correlate the errors that you obtain over time from the sampling to the specifics of the sampling?
For the specific what?
So, for example, in corona surveys or in any of the other ones that you do, the error varies over time, right?
No. I wouldn't see any.
If I see the plots, like the error.
In the peer-to-peer, you mean?
Yes, in any one of them, the error.
No. The short answer, no. We didn't see any particular correlation. We did find biases in some experiments we ran. For instance, we ran a survey for an election in Chile, in which the sample was obviously biased to the young voters, and the outcome was very different from what other surveys were saying. And we detected it, and it was clearly because of that. And in the paper we just published about elections, we observed the same thing in Spain. Mm-hmm. Essentially, we were not stratifying by age in the initial attempt, and then we decided that we have to stratify by age, otherwise the results would not be good. And the problem is that you cannot correct that afterwards, because the fact that one person is answering the survey has a given age, it doesn't tell you anything about their community. It can, but.
I was guessing that in IPFS you have a similar issue, right? Like the underlying network topology is what it is, mm-hmm. And if you don't take that into account, your sample is not that random anymore.
Yeah, actually, IPFS is extremely nice, because it's almost, and we plan to do an analytical study, but it's almost as this random graph model that I presented, because it's man-made. So and hashing is almost as a random generator. So it's quite nicely distributed and built.